So now let's talk about how we find a description of C that uses arc length as a parameter. So we're going to start with the way that the arc length parameter is related to this time parameter. Here we're starting at t equals 0. We'll go up to time t. And we have to integrate this speed. So this is how s and the given parameter t are related. And remember, we found in the last part of the problem exactly what that magnitude is. So this s here is just going to be the integral from 0 to t. And now I'm going to use that expression from before, which was the square root of 9. Now, instead of a t, I'm going to replace that t with tau, plus 13 tau squared. D tau. So this relates s and t. So what I want to do is I want to compute that antiderivative first, and then then use the fundamental theorem of calculus to find exactly what s is in terms of t. So in order to do that, we need to evaluate this definite integral. So I want you to take a second and think, well, how should we go about doing this? Okay, so there's a little trick here. And the trick that we have to see here is that both of these guys have a tau squared to give up. And the nice thing is here that remember that square roots can split up over multiplication. So I can actually rewrite this as the square root of tau squared times the square root of 9 tau squared plus 13. Since tau is between 0 and t, and we're assuming that t is positive by how we've written this right here, we know that the square root of tau squared will just be tau. So what I can do is I can rewrite this as the integral from 0 to t of tau times the square root of 9 tau squared plus 13 d tau. And now this is an integral that you should be able to do. So there are different ways of maybe looking at this, but the good approach here is to note that the 9 tau squared plus 13 is a great choice for u. We can do this integral by a u substitution. So we can do a u sub with u is equal to 9 tau squared plus 13. And if you actually do this u substitution, you can work through the details, and I advise that you do that, but I'm just going to let you know what the answer should be. Okay, so if you did that u substitution, this is precisely what you should get. We can now finish this off by substituting in our limits of integration. So we find that our s is equal to this expression that I'm writing down now. When we plug in tau is equal to 0, we get 1 over 27 times 13 to the 3/2. So this tells me precisely how my original parameter t and my arc length parameter s are related. So in order to re-describe this curve, I mean, if we can evaluate this integral, that is actually a semi-big if, but we could here, we now have s explicitly as a function of t. To re-describe this curve using arc length as a parameter, we need to find t explicitly as a function of s. So the next thing that we need to do is we need to find t in terms of s. And we do that by solving this above equation for t. Now that in itself is not going to be the most pleasant thing in the world, but let's start by just adding this 1 over 27 times 13 to the 3/2 to both sides. We can now multiply both sides by 27. To get rid of this 3/2 power on the right-hand side, we can raise both sides to the 2/3. Now we can subtract 13 from both sides. That'll leave us with a 9t squared on the right-hand side. We can divide by 9. That'll leave us with a t squared. And then we can take a square root. So that's what I'm going to do, sort of all in one fell swoop here. So, as I said, we'll first subtract 13. We'll divide everything by 9. Now we have a t squared left. So we'll take a square root. And we should take a positive and negative square root, because anytime we have something squared equals something, we have to consider both the positive and negative square root. Here, since we're looking at positive times t, we can ignore this guy. But I did want to emphasize that you do need to consider it. So here is t as a function of s. And yes, it looks terrible, but we can do it. Okay, so we found this expression for t, and now all we have to do to redescribe this curve in terms of s is to take this expression for t here and plug it into this original description of the curve right there. And so when we do this, I will indicate this by an r of s, meaning that we are describing this curve in terms of the parameter s. And when you take this awful expression for t and substitute it in for the t's up here, you're going to get, so you get this expression. Now, I've done a fair amount of simplifying here. What I want to emphasize here is this is really just an exercise in tedious algebra to get it to this point. Don't be bogged down by how awful this thing looks. What I really want you to look at is realize that this arc length reparameterization is really, really, really messy. This is the sort of expression that I like to comment that it's really only something that its mother can love, and I think you can kind of see why. But the point that you should take out of this is that that original description that we have right here is nice and easy. If you want to work with the curve, you probably want to work with this. You definitely do not want to work with this. But it brings up an important point. So one, whenever we're doing these arc length problems, they may give us ugly answers, and at best, we can at least do this problem. Sometimes, though, we can't. However, arc length is very important as a theoretical parameter, and I'm going to try to at least sort of convince you about that in the next slide, as well as give you a few thoughts about this process. But the point of this is that in order to reparameterize a curve using arc length, what we have to do is we have to compute s as a function of t by evaluating a definite integral. We then have to solve for t as a function of s, and once we do that, we just plug that expression, no matter how messy it is, into the original description, and that'll give us our reparameterization in terms of arc length.